Hi, we'll get going. I'd like to thank everyone. There's a lot of people in the room here today. I know it's getting later on the second day. I appreciate that everyone's still turning up to listen to talks and getting some value here. So today I'm going to do a talk called Things That Pause and Why They Hurt. It's going to be talking about different pauses and how things happen. But just before we get going, my name's Charlie Gracie. I am a principal architect on a new Java platform team at Microsoft. And I've been working on JVMs and particularly GCs for almost 2 decades now. So dealing with and recognizing pauses in applications is kind of what I've ended up spending a large portion of my life doing at this point. So it's very near and dear to me. So hopefully this talk helps you guys see some common traits that are happening in new microservice architecture deployments, and hopefully you can take away something to help move forward. So quick agenda. I'm going to talk quickly about some things that pause, maybe 1 or 2 things most people won't consider pauses in the past, and hopefully I can convince you that they are some pauses that are something you might want to consider going forward. Measuring the impact of those pauses across different types of workloads, so starting kind of with the old traditional monolith style workload, and then kind of how you can measure that and the impacts they have on a microservices workload. And then I'll answer my final question before we're done. Are microservices evil? So we'll get going now. So quickly, why do we care about pause times in our applications? Well, the probability of seeing the longest latency that your application will have is kind of a function, in my opinion and some of my colleagues' opinions, on the number of requests that you have of downstream resources. So a given transaction might just talk to one service and get back an answer, and that would have a particular maximum pause time latency. But then as you add more and more of these service nodes, a request for the transaction, it'll kind of change what the latency is that you'll see in your application. So very quickly, I just have a simple calculation there that if you had a transaction with 2 requests and you cared about your 99th percentile, there is about a 2% chance, so 1 in 50 of the users of your application will now end up seeing that pause time when they go to your system. Depending on your average pause time and those things, people like to click on their results and see the results. They don't like to wait. So if some large portion of your users start having longer pauses, you may start losing a lot of business. Okay, so things that pause. So the first thing, we're at a Java conference. Most people here are working in Java. So the JVM is one of the major causes of pauses in your application. And there are things that I like to call like sort of scheduled maintenance and things that are sort of more of an on-demand maintenance. Scheduled maintenance in the JVM is a lot of the time handled by save point pools. So by default, in every JVM, threads will check every 1 second to see if there's things that need to happen that it should be doing to perform maintenance to be able to keep on moving and keep your system in a healthy state. So with that 1 second, every 1 second, every individual thread will have at least a minute pause while it checks the time. May not be that huge, but it's a thing that happens, and then it could go off and do further work. On-demand pauses, the most common one most people are going to be aware of, is garbage collection. It's probably the biggest impact on latency for most applications, and it's because it can be really big depending on your heap sizes and GC tuning and those things. But there are other on-demand pauses in your application. When the just-in-time compiler actually goes and creates code to make your application faster, sometimes it has to make changes to that or undo the work. So there's de-optimization events and other types of maintenance like this that will also actually then cause some application pauses to happen. Another major cause of pauses in your application is, again, most of these are maintenance related. This is related to the operating system itself. So operating system for doing things like page reclamation. If you're doing lots of small like native memory allocations, malloc and free, it might have to go compact those spaces. And there's a whole host of other reasons why your OS actually may get in and pause your application, or at least make it appear that there's a pause. Of course, there's downstream services, your database. That could take a while. And as you move towards like more microservices relying on each other, there's a whole other JVM in the picture. So everything that could cause the previous JVM to have a pause, well, you can now be a witness to that in yours as well, along with any other ones down below, including databases. So one of the ones that a lot of people don't consider when they're talking and thinking about pause times or delays in their application is actually resource contention. And we see this a lot on systems when you're getting into highly tuned JVMs and you're really trying to push your CPU to the max and hit 100% CPU utilization. You'll see a lot of things around some blocking operations. And the one that I think is the most commonly missed is physical resource limitations. So when you get down to the layers of like your socket, your networking devices, and you're trying to do socket resources and things, a lot of those, your physical machine has one. Maybe it has 2 or 4, depending on the type of device that you're dealing with, but there is a small number of them. So when you're running on a large CPU, if you start to have a lot of your application depending on those, then you can start to see to your end user a pause. You're not really paused, you're just waiting for something to happen, but your end user is going to go, well, I had a 10 millisecond delay or a 20 millisecond delay, why? And you could come down to figure this out. And this all kind of comes back to Amdahl's law. And we don't really have infinite compute environment. So before you can go study what's happening, you need to kind of attribute the pauses in your application. So the first thing, I said the biggest concern to most latency in applications is going to be your GC. So one of the things you should be doing is always kind of gathering GC logs so that you can perform analysis when you have, say, some delays you're measuring in your application. Maybe you could attribute it to GC pauses. You have to tune your GC or do other things to move past that, but having the logs help. For doing some work and understanding other things like happening in your operating system, I've just listed 2 quick tools here, IOStat and VMstat. There are a whole host depending on which operating system you're on, but these are, again, things that if you're monitoring and you happen to see a pause, you can go back and try and attribute it to maybe spikes in something else that's happening on your system at that time. And of course, if you have databases or other downstream technologies, whatever monitoring they happen to have. And I'm talking about gathering these things, and it'll hopefully become clearer in a few minutes why, because I'm not listing very much here. It's a few things that I'm saying you should have. There's probably a whole host of others. This is not inclusive on monitoring your application and your machines, but it seems like a small set, and it is a small set for what I usually start looking at, but when you're using one machine, it is a small set. Now, when you start to have multiple different layers of requests going through one another, it's the same small set, but it's a whole large set of things, and trying to attribute where those happen becomes a much more difficult problem. So, measuring the impact. Everyone's seen a simple picture of a monolith. If I put the white square around, yes, it's white square. That's simulating that those 3 things of my application are all just in one process. Even in the monolith days, maybe things were out into 2, or a third one, but this is kind of the story that everyone's telling, and it's a picture you see if you search monolith versus microservices. You'll see a very similar picture everywhere. When you have transactions coming into your monolith, there's one thing to go watch, one thing to measure. If you happen to have, and I'll just kind of talk about GC, and probably for the rest of the talk, I'll mostly focus on GC pauses, but whatever I say about GC pauses can attribute to the other types of pauses that are happening. But let's take, for example, you have a monolith application that has a 5% overhead in GC. You might say that's really high. I'm going to argue that when people believe they're at 1, 2, 3% overhead in GC, they're measuring the entire lifetime of their application for the log. I'm saying when you're in the critical, intensive part, it's probably closer to 4 or 5%. So if your application is spending 5% right now in GC, 95 not in GC, what percentage of your users are probably going to see a pause, be impacted by a pause in your GC? It's about 5%. So it's kind of easy to figure that out. You can look at it, everyone can come up with that. I'm not telling anyone here anything they didn't know, I don't believe. So what now if we move to microservices? Again, I assume everyone's seen this picture, probably right beside the monolith one on a website, describing, hey, why don't you break up your application into these smaller disjoint pieces? It's easier to write your code, you keep things modularized, it's wonderful. They're not wrong. There are actually lots of benefits to working in this type of environment. But if I asked you to look at this and assume all of the blue things, microservices or JVMs, they all have we'll stick with 5% GC overhead. If your user requests something into this application, what is the percentage of your users that will see a GC pause? Anyone off the top of their head, making a random guess? It's not 5%. It's getting closer. It's not 5 per, so it's not a sum up. But with the numbers when we're looking at it, it's probably closer to 35%. In this example with the 4 microservices. Follow-on example, another growing out the chart of microservices happening. Seems to be a very easy progression as I'm talking to customers and seeing different workloads. They had a great success by turning a few parts of their application to microservices. Oh wait, let's divide this one up because it's disjoint, so they split it into something like this. When you look at an application like this one, it has 10 microservices. And from up to this point, this is really common, in my opinion, from workloads I see. So we're up to now at about 60% of your users are going to have a GC pause. So at that point, if your normal transaction for somebody was 50, 100 milliseconds, and your average pause time was, let's say, 100 milliseconds in your GC, or 50, I'll be generous, 50 milliseconds. If you had a 50 millisecond transaction, a large portion, over 50%, now are seeing double the time it should take to get there. That's maybe not so bad, but it starts to really add up as you go on. Here's a picture, another chart. This is not an exaggeration for workloads I've seen and the way people have divided up their application. I actually wanted to do more. I was worried you wouldn't be able to see all of the pictures and see what was going on if I actually made it represent some of the workloads I've been looking at. So to go through in this one, there's 24 microservices. It's not exactly representing a workload I saw, but we've seen chaining this big. I just tried to make it fit in the picture. When you have something like this, you're starting to now go above 90% of every user to your system will see 1 GC if you're at a 5% GC overhead across them all. If they're different, tuned slightly differently, it's slightly off that number, but it's going to start to approximate 90% in most workloads that have a setup like this. That you're going to see at least 1 GC in every transaction that comes into your system. So that's not great. It goes on. I've seen ones with over 500. I don't even know what their length of time to do that transaction is, because just deserializing and sending your transaction information across every time, maybe it isn't even impactful to have a GC show up in there because their whole thing is so long now, but you still would have the possibility of 1 or more GCs really impacting a large portion of your users. So how are we kind of calculating? I've been throwing numbers at like 35%, 60%, 90%. What are we calculating this based on? So One of the first things that I want everyone to think about is, depending on the number of nodes you have in your system, when do you have opportunities for GCs to happen? So transactions on its way in, you come up to the first node. Well, on your way in, maybe it's in a GC while you're in the middle, when you contact it on your way in. During processing, it has GC. So one chance of a GC for the first node. 2, again, 2 GCs, 3, 4. Now, you haven't actually answered anyone yet. It's in theory a whole new request on the way back because it's one JVM talking to the other JVM. So that's another opportunity, in our opinion, for another garbage collection to happen. And so on till you get back. But talking to you, I'm assuming your client, that's your responsibility if it's GC. So we're saying that it is about 2 times the number of nodes minus 1 possibilities of a GC that could happen, like throughout your way. That's depending on transaction length of things. This number is off, longer, shorter, but just to keep things simple, it's about this number. So that is the opportunities for GC. If we then wanted to go look at what's sort of your total GC overhead to start filling in numbers for our calculations, I wanted to start here and build kind of a simple tree structure of how the decision makes at a per node level. So every time I put a new level in the tree, that's representing another node in the call chain. So first one, I'll keep with my easy numbers of 95.5. If you hit your first node, 5% chance. We'll go down the left side of the tree that you hit a GC, 95% on the other side. Node 2, same type of decisions, continuing to come on down at every time we hit a new node, in a GC or not. And then we kind of get down here to this sort of total overhead for your GC, in this particular case with 3 nodes. And what this is really telling us is there's one path through that set of nodes where you could have no GCs. There's one path where every single node you hit a GC based on these percentages, and then there's 3 of each of the other paths. So the claim here is that we can use, for a simple where it's a fixed number of a GC overhead per node, it's kind of a simple binomial calculation to figure out what the percentage of time would be in your GC. Of course, this calculation can be modified, improved, and it's easy enough to do to handle different amounts of GC overhead per node, but I just want to keep it simple and keep things easy to go here for today. So the next thing I want to kind of show people is to kind of put some charts, and demo might not be the right word, maybe charts, of this little graphing tool that people on my team have developed. The main contributor was Kirk, who's sitting over there. This is his GitHub repo for the model. So you could go get it right now during the talk if you want, and start asking me questions about it. But you can go get this, and it kind of will take you through the 3 different sets of decision making we've used to kind of come up with these numbers and follow through with the model. So just 1 second quickly here. So I'll quickly, oh, not on your screen. Hold on. Sorry about that. All right, let me make this a bit bigger. So this first chart and graph that I'm going to show is just, this one is the simple calculation of how many nodes do you have in your system with your GC overhead, and what's the percentage. This calculation is going to probably be a little backwards to what you're thinking, but it's the way to do the calculation. Is what's the percentage of users into your system that will not see a GC. So on the left side is the percentage of no pauses, and across the bottom is node count. So if I have 100 nodes, I could put it at 20 or 5, and that chart would just be a lot smaller, and I'll zoom in here in a second to show a smaller one. But basically what this is showing here is that the more nodes you have, you start to very quickly at GC 5% overhead approach where every user will basically see a pause. And how big is that? Okay, it's big enough. So if I switch to 20 nodes, you can see that quite quickly for 50% is about 7 nodes. So 50% of your users won't experience. Clearly the other 50% are experiencing it. So that's not a very deep call chain to actually have this percentage happening. If you switch it down to 3, you're like, I do a much better job with tuning my GC. It adjusts it, but looking at this chart, it's still a very high number for you. So this information we use here feeds into some of the following charts as well, but I just wanted to bring it up because it very quickly can show you how impactful chaining these nodes will be to your end user and how much that will possibly drive them away from your application. Let me see, switch to the second demo. I'll make this a bit bigger again. So we'll start with 20 nodes. So what this one is calculating based on your node count and your GC overhead is the number of pauses, the percentage of the number of pauses that a user might see based on how many nodes you have. So at 20 nodes in your system, a reasonably large percentage of users will about almost, it's too small for me now, above 50% will see 1 or 2 pauses total. They're both at 27% or something. They will see, that many people will see 1 pause, but also 27% will likely see a second pause. So if you're at a 50 millisecond pause, a lot of these users are going to be impacted by 100 milliseconds just to get through the chain of nodes in your call stack. And you can see other numbers. For 3 is down just over 17.5%, so it's probably 18%. And then it kind of fizzles off quite quickly to be approaching a 0 chance. But again, this is here, and it is kind of an interesting number. I'll show 5 because this probably looks like more what people expect. A flat downward curve from the number of pauses, but as you increase the nodes, you really are increasing the number. And so one of the more interesting ones is if I move it up, enter doesn't work, to 30, you can see it slowly moves up again more. And the interesting thing is, as you continue to add nodes, that wave that looks like it's going across now, because that's there, that just continues to follow across the page. So as this gets deeper, there is a large number that we'll start to see 2, 3, 4, 5, 6 pauses quite quickly. I'm not sure many people here are going to have something with 50 nodes regularly in their call chain, but at that point you do have a very, very large number. And to me, I was very shocked at this line of data when we first started showing it. I always thought it would continue to be a hockey stick, but it makes a lot of sense once we started thinking about it. So the third chart here that I have for sort of explaining through the numbers I was telling you guys earlier is this chart. This one has some more input, so if I put it up and anybody wants me to try something so you can see something, feel free to yell out. So it's number of nodes again in your system, GC overhead, average pause time, the actual time it's taken, and an arrival rate of how many transactions you have to your system per second. And what it's going to compute is the GC latency effect on all 1,000 of those transactions into your system. So we're using the details from the calculations in the previous charts to go through and calculate this. Let me see, try and make it a bit bigger. I didn't refresh. There we go. So you can see that of your 1,000 requests, there is a very high peak right in the beginning, sort of like a cliff of no pauses. Of course, there's a reasonable percentage here with 20 nodes that there won't be, so you have like 180 that won't see a pause. But then because I'm saying the average pause time is 100 millis, every sort of 100 millis after that, again, you see a cliff, but they're not actually falling off as quickly as I personally thought they would before we started digging into this data, which is very interesting and does match up with like complaints and performance tuning that people are having to do with their applications just for the fact that it's actually this peak. So to me, it's really interesting that you can see even up to like 100 milliseconds on there, you're having 50 or more of your transactions in that range of the incoming per that second that are actually going to have this. That's a large number, and the fact that there's still a lot over at 200 and then even a bunch more over at 300, it's very high. Again, I'll do a quick change because a lot of people will tell me this is probably more accurate to how their application is running. So it does shift down reasonably quickly. There we go. Sorry, sometimes the numbers are too bunched. It does shift down, but you can see there's still a cliff at the different 100 milliseconds. But at 20 nodes with the lower GC percentage, we're maxing out at 300 millis. There's very low chance of actually having the fourth pause at that time. So let me get rid of this. Go back. All right, cool. So we're back here. I just really wanted to show you that chart. And if you're working on a system where you're starting to deploy these types of changes, you're moving down from a monolith to microservices, or you're actually just starting from scratch, it's a very good way to work from the ground up, and that way on something new. Think about what the pause time implications will be. And I've been focused on GC here because it's more of a consistent, easy number, and it's my background. But you kind of have to consider all the other types of pauses that might also be happening as well, and you can kind of come up with an average and run that through. For myself, looking at a workload with these now, I will take probably the 5% that I think it's at and under heavy load versus a 3 and kind of average them out myself and be like, that's probably more what our average user really sees, but I'll just kind of blend the versions of a few of the pieces of data myself. So I'll come back to my first question. Are microservices evil? No, they're not evil. But because they do bring a lot of benefits, I'm not going to spend, there's multiple people's talks that are a whole talk, maybe even longer than an hour, about explaining the benefits of microservices and why to go there and why to use them. But I'll cover a few points here. Like, a lot of the decisions that you do moving that way, like modularizing your application, I see huge benefits in that. You have small, more discrete pieces of code. It's easier for people to work on those pieces of code. Sometimes speeds up the development, but the one thing that modularization and autonomous teams doesn't really bring you, it's not a substitute for code quality or for design discipline. A lot of people are kind of confusing those things with moving to microservices. They're like, you kind of get that for free. Bad design, bad architecture, you just have a smaller version of the same badness over there. So it's not just fixes your program for you or fixes all of your problems. It's still something that requires a lot of thought, and in my opinion, more thought, because now you also have a lot more infrastructure to plan with as well. Another win was, like I said, was the autonomous teams. You're working on smaller pieces. It really can help you with scale out issues or scaling out. And I'm at a Java conference. I don't know if I should say it. It gives you some flexibility in technology. Not every one of your microservices has to be written in Java. They should. I love Java. That's where we should be writing them all in. But if there's a fit-for-purpose piece that's better off as something else, well, since it's not one application, you're free to go do that. Try it out. Make things work that way. All right. So, a longer recap here. So, going back to some of my first slides, what I really want everyone to do is sort of understand the trade-offs that you're making when you're moving through things. Some of your user interactions, they're really key to your business model. You don't want to be disturbing the visibility or the user reaction to coming to your website or hitting your app or however they're involved in your application. So you really need to sit down and understand how those decisions impact the people that will be using your system. Also, understand how those decisions impact your system. There may be very good reasons to divide something up. So I really think, and everyone should stop and separate where it makes sense. Because you're moving to this microservices architecture, don't go, everything we do is a new REST API. It's all on its own, it's one thing. That may not make sense. If you have a single microservice that only one other microservice talks to, it only talks to one other one, and then they all send back the answer. Having those separated as logical units might make sense because you have a clear API design and things at that point, but can those actually work together as one process? Can you bundle them in a single application? I think in a lot of cases you can. When I put up the chart, I won't scroll back because it's far, of the 24, 50, 100 in a row, when we've looked at the applications that those are representing in my charts, maybe they needed 4 or 5. They just really decided that every team would do their own complete microservice, and then they would just talk to one another. They didn't have to communicate as much in teams, not that they were missing communication, but it just made things so much easier for them to drive through and get through their work that they ended up this blown up picture that was almost as unmaintainable as then in the end as some monolith that was complicated for other reasons. So in the end, there's no one-size-fits-all solution in this area. I didn't come into my talk here to say don't go down microservice path. I didn't come in here to say monoliths are the future. I read a great blog post the other day that someone said that's the future of development. I think they were trying to be somewhat getting people to look at it, same as I was with saying are microservices evil? Have your pitch to get people to want to listen to what you're talking about. But I don't think anyone believes that's either the right answer either. I think that proper designing and proper fundamentals is probably where we need to go. But when you do start to do these things, please think about the overheads that you will incur with those deep chains. It is so often quite large, and it's a hard thing to kind of diagnose because you're now monitoring 20 systems and trying to match up why this one user's was long. There is lots of sophisticated tooling for that as well, and they're doing a great job of getting that going. But for me personally, whenever I can, I want to try and clump 2, 3, 5 of those, what people were subdividing out, into a single sort of macro service. Maybe that'll be the title of my next talk, Macroservices are the future. All right. So I apologize, I spoke way quicker than I thought. I hope people have questions. So I'll open it up for questions since I spoke way too quickly. Oh, right here?
Yeah, it's a very interesting question. It's a trade-off to find out what's the optimal number of divisions.
Mm-hmm.
There are two things that I think would be interesting to study. One of them is that obviously the GC parsing and a lot other factors are influenced by the size of the microservice. Of course, if you split it up bigger, it's likely to become less frequent and less the average duration because you're garbage collecting less. So that would be interesting to sort of correlate so you can find some kind of sweet spot or something like that. And also to incorporate, there are some fixed delays when you split up like network latency, deserialization, that you would sort of have to count in when you're trying to find, is this a sensible amount in microservices? Is that the right SWOT? Or do we having too many or maybe even too few? So that would be a little bit interesting to sort of have in this kind of graphs where you can maybe find a little bit like here we have a sweet spot.
Yeah, for sure. Yeah. The first question, I guess we'll repeat and then.
You hear me now? Okay. So I was just saying that I think it's very interesting this to find this sort of like what's the right number of microservices. And I was just saying that I think there are two aspects of that that's interesting to take into this picture. One of them is that as the size of the microservices shrink, the probability of, for instance, GC, but all the other, and the average duration of GC is probably going down, probably not linearly, but there is some factor there that would be interesting to study. But also then additionally include the fixed aspects of the latency, like network latency, deserialization. If you start putting those factors in, it could be quite interesting to find out. Maybe there are some interesting points there about the sweet spot, like this number is too big, this number is too small even sometimes.
Yeah, and for the first one, about heap sizes and GC influence there, kind of one of the ideas that most people employ as they move out is since they're dividing their application up, they tend to actually use less heap. So if you had one big one using 24 gigs, now you have 10 small ones using 2 gigs. So generally those kind of keep similar types of profiles, but it depends on the ratio you use and how things are working. But one of the things I've noticed on a lot of these areas, now that you've added all these extra levels of communication, whatever your communication is, so you're probably serializing objects on one side and the other to send them back and forth, that actually puts more, doesn't make your GCs longer, but it will tend to give you more frequent GCs possibly even than before in the other one. So in theory, your longest tail latency might be a bit smaller, but you might actually be now getting more tail latency events because you're GCing more frequently. But it's all trade-offs of things that have to measure. So one of the things that we really talk about and that we can do is like even per node of what's happening for amount of GC and things, and they do shift the charts. I would suspect if I looked into them, but I think the average it's the same chart, just either up or down a little bit. They're quite similar. But to the second point about measuring the overall sort of like what it is to make your transaction at that point because you have extra network communication and those things, yeah, it's an interesting point that I was looking into and that I assume other folks are looking into as well. I saw it mostly as a net negative because it's always an increase it's not always, but generally when I was looking at it, you felt like you were always going to have, if you took out any latencies, the actual length of time to get a full transaction done was always longer because you were dividing it across all of these ones, mostly because of the network communication. If there's 4 or 5, it's probably longer than doing something in your same process for getting data. And then a couple of those cases when they're actually very important, that's when I'm recommending that you actually, if those ones don't have to be separated, put those 2 or 3 that have a lot of communication together, remove the network communication, and now you're actually good. So it's a way, keep your microservices, but have a few that are now sort of co-located. That's the way up. Any other questions? Oh, one there.
Hey, I was just wondering, have you seen any occurrences where you've met like clients or people who have actually overused microservices and have actually started merging them back into bigger applications? And how has that worked out?
A lot of the people I'm talking to right now, we're just still convincing that they have too many nodes in their along their pipeline. In some of my past experience, previous job, we were able to convince, it wasn't even at the microservices time yet, they were just already doing this type of thing. We were able to convince them just for the sort of the increased transaction time to move a few in. But I believe there's been talks by a few large corporations, I won't say name because I'll probably get the wrong name and it won't be right, where they actually did go down this path, and they then were out talking to people about how they merged so many of them back in. They kept their individual work silos, but for each of the things, but they ended up moving a lot back. And if I'm not mistaken, the person I'm looking at, I'll dig up the talk and make a note with mine about this one. But I believe they were saying somewhere around like 3 or 4 was actually where they started, things were good for them. And they had wins because a lot of their front gates or like things in the middle of their flow, then they had multiple versions of those, but a lot of the rest they didn't need, so sort of co-locate those ones. And then they saw some really drastic reductions in overall latency of their application. Okay, if there's no other questions, I thank everyone so much for your time, and I hope you enjoy the last 2 sessions, I think, of the conference. Thank you.